Okay, so this is something altogether different than what we have done in the previous sections and the previous modules. Here we're going to be looking at improper integrals, and these are integrals that either have infinity or negative infinity as one of the limits, or there's a point inside the integral, inside the interval, where the integral is not continuous. So we're going to evaluate an integral over an infinite interval. We're going to evaluate an integral over a closed interval with an infinite discontinuity within the interval. And we're going to learn about the comparison theorem and see how we can use it to determine when an integral is convergent. Okay, so here's some examples of some improper integrals. The first being, and now I remember why this was wrong. This is supposed to go to infinity. Okay, so the integral from a to infinity, that is an infinite integral or an improper integral. The integral from minus infinity to b, again, improper because I cannot put negative infinity into the limit. I'm sorry, into the evaluation of the function. And then negative infinity to positive infinity, same problem. And then here's one where, as you can see, I have 1 over the square root of x, the integral from 0 to 5. So why would this one be an improper integral? What's wrong with that? Everything looks like it should be okay. What's the problem? Anybody have an idea what the problem is?
One part of limit is infinite, another part is finite.
Okay, so here at 0, you're going to get 1 over 0. So that this function is not continuous at this limit. Now we can evaluate this limit, but we have to do it a different way. Okay, so so thank you for that answer. So the first thing I want to do is define what means for an integral to be convergent. So the definition of convergence is we have an improper integral is said to converge if I take the integral from a to positive infinity and I get a finite number. So notice I actually get a number L. So if I get a number that is not infinity, then the integral converges. All right, if I get infinity, then the integral is said to diverge. So how are we going to compute it? Well, if it's the integral from a to infinity, I'm going to put a t at the infinity spot and then take the limit as t goes to infinity of a to t of whatever the function was, and then check to see if I get a number or check to see if I get that something that goes to infinity. Same thing, if I have the integral from negative infinity to b, I can put in t to b, and then I can let t go to negative infinity. Uh-oh, there's a negative missing. I can let t go to negative infinity, or I can make this minus t and make it go to infinity. Either way, same difference of the function f of x equal to L. Again, looking to see if I get a number, any number that is finite, anything other than infinity. If I get infinity, then my integral diverges. Okay, so here is our first problem. And we're going to use this technique. It says find the area under the curve of the function f of x equal to 1 over x on the interval 1 to infinity. Okay, so let's draw this. Okay, so we said on the interval, so at 1, the function is 1/1. And then it decreases as x gets bigger. So we want to find this area, which is the area underneath the curve. And this is just going to keep going. Okay, so we want to compute that. All right, so that's going to be the area. It's going to be the integral under the curve from 1 to infinity of 1/x dx. Now, how do I deal with that? This is the limit as t approaches infinity of the integral from 1 to t of 1/x dx. Now, I need somebody to give me what this, how to integrate this right here. How do I integrate that part? What's the integral of 1/x?
Natural log.
Natural log. Thank you very much. This is the limit as t approaches infinity of the natural log of the absolute value of t evaluated between 1 and t. Now I'm only looking at positive numbers because it's going to infinity. So I'm going to drop the absolute value. So this looks like the log of t minus the natural log of 1. Okay, somebody tell me something about this. Give me something. Anything. Something about the log of t or something about the log of 1. Okay, we learned a lot about logarithms. Do we remember it? What's the log of 1?
Is it 1?
Okay, let's draw it. Okay, that's the logarithm function. That's the natural log. So what is the log of 1?
0.
0. Thank you. Brian, do you see that? Brian.
Yep.
Okay, it's
You're
right
talking
here.
about say, I'm sorry, where are we looking at?
The log of 1, you answered, and I wanted to make sure you understand that the log of 1 is 0.
Okay, and we know that based on the point that you marked?
Yes.
Okay.
Okay. All right. And what happens to the log function as t goes to infinity? What does the log function do? Just from my picture. Come on, guys. Jump in here. Is the limit 0?
No, it never touches 0, right?
Is the limit 1? Where is it? What is it doing as t goes to infinity? That function is going to infinity. Okay, so since this thing is going to infinity, we say this integral diverges. Okay, does everybody see that now?
Yeah.
Okay, thank you. All right, blast from the past.
Wait, Dr. Locke, can you scroll back to that problem?
I will.
Thank you.
You mean here?
Yes.
No problem. Okay. So now we're going to take the volume. Oh, the volume of revolution. So we're going to take the solid that we have in the last problem, and we are going to take that area and we are going to revolve it about the x-axis. And when we do that, it will give us a volume. Okay. All right, there's my picture. So I'm going to revolve this about the x-axis. That means I pick a point and then I revolve it about the x-axis like so. And then over here, I also know that this curve is actually being revolved. So now I have a three-dimensional solid that has volume. Okay, so let's go back to when we did volumes of revolution. What do you see? I see something inside that circle. What do you see? What does that become? And what method am I going to use?
You're going to use the disk method.
I'm going to use the disk method because I see a disk. All right, so we are going to use the disk method. Anybody remember the formula for the disk method? The volume is equal to what? Disk method, the volume is equal to
2 pi.
okay, 2 pi comes up in the shell method, or if I'm doing surface area of revolution. This one, we're going to use the area of a disk. And what's the area of a disk? You guys remember that? Here's a disk.
Pi r
So
squared.
is it?
Okay, I think I got about 3 people chiming in now. Awesome. Okay, so yes, it is pi times whatever the radius. Here's the radius or the height of the function that's going by. So the area of this is pi times the radius squared. So over here, we get the integral from a to b of pi. And again, you are right, times the radius squared dx. Okay, so for this problem, what is the radius? The radius is the height. So what is this height? What's the height of the disk?
Is it f of x?
It's f of x. It's the function value. Okay, good. So we're getting somewhere. So the volume is the integral. We are starting at 1. We are going all the way out to infinity. We're doing pi, and the radius is the function 1 over x. We're squaring that, and then we are doing that dx. So does everybody see what the integral is? Okay. So we use the disk method because when we did a volume of revolution, we saw our disk or our circle. We know the area is pi r squared. That means we need to find the radius. The radius is the height of the function. Excellent, excellent, excellent. Okay, so now we need to do this integral. So this is the limit as t goes to infinity of the integral from 1 to t. T is what's going to infinity, the integral from 1 to t of pi. And to make this easier, why don't we write this as x to the -2 dx, because now it's much easier to integrate. So now we get the limit as t approaches infinity of, when we integrate this, we get pi, but now I'm going to get x to the -1 over -1. So I get negative pi x to the -1, and that gets evaluated between 1 and t. So we have the limit as t approaches infinity. When I'm going to get negative pi, then I'm going to get 1 over t, because that's the t to the -1. So I get 1 over t, and then when I put in 1, I get minus or -1. Okay, now here's the fun part. How to take the limit. Tell me what happens when you take the limit as t goes to infinity. What happens to 1 over t as t gets very, very, very large?
It approaches 0.
It approaches 0. So if this goes to 0, then my answer just looks like negative pi times -1 is pi. This is less than infinity. So this integral converges. So although it goes all the way out to infinity and keeps going, it has a finite value. So the integral converges. Any questions about that? Okay. The next problem is a toughie, but we can handle it. Okay. All right. We need to compute this integral. That is the integral from -infinity to 0 of dx over x squared plus 4. Let's rewrite it in the proper form, because right now it's improper. So we're going to write the limit as t goes to -infinity of the integral from t to 0 of dx over x squared plus 4. Okay, so I need somebody to tell me what this piece is. How do you integrate dx over x squared plus 4? It should look familiar.
Is it the sine of a over x?
Who's talking?
Brian.
Brian. Okay. Okay, so the sine one, so first off, I can give you this. It's going to be an inverse trig function.
Is it the tan inverse?
Okay, so it's going to be the tan inverse. So the sine, Brian, is the one that has the square root. So the sine looks like this, has the dx over the square root of 4 minus x squared. This one gives us sine. Okay, so that one, this integral would give us sine. This particular integral is going to give us tan inverse. Okay, so we end up getting the limit as t approaches negative infinity of 1/2, the tan inverse of x/2 evaluated between t and 0. Okay, does everybody see how that works? That block became this antiderivative, and it gets evaluated exactly at the limits. Okay, so the reason why this one is tough is because this one is tough in the way that we have to think a little backwards. Okay, so this is now the limit as t approaches negative infinity, 1/2. I'm going to get the tan inverse of 0 minus the tan inverse of x/2. Okay, so tan inverse of 0, that's what I need to find, the tan inverse. So I'm going to draw the tan inverse function for you. I know many of you just don't walk around thinking about what the tan inverse function looks like. Well, I'm actually going to draw the tangent, not the tan inverse. I'm going to draw the tangent function. So here's the tangent function. Let's see, I'll draw this over here. Okay. So the tangent goes down like that, comes up. And so that goes up here forever and goes down. This value here is -π/2. And this value is π/2. Okay, so the first thing that is this, let's call it y1. So y1 is going to be the tan inverse of 0. Remember, we're trying to find y1. We're trying to find that thing. What is the tan inverse of 0? So if we take the tangent of both sides, we get that the tangent of y1 is 0. So what is y1 then? If the tangent of y1 is 0, what is y1? You have the picture, you have your own recollection knowledge, and you also have the quick study guide, which has all the values on it. So which angle has tangent equal to 0? All those three things to help you.
Isn't it pi?
Okay, where do you see pi? So this, the red function, so I don't even have to go out that far. This is the tangent of x. And notice this function doesn't go all, I didn't bother to do the rest of it. But yes, you are right. Now that I think about it, Brian, you are correct. y1 could equal pi. The only problem is tan inverse has to be between -π/2 and π/2. So although pi is a correct answer, it is not the correct answer. We have to use this angle right here. We have to use 0. Even though pi works, we have to use 0. So y1 is going to be 0. So now I know that this piece takes off and heads to 0. Now let's figure out y2. So y2 is the hard piece. That's this piece. Okay, so this is y2. All right, so y2 now has the tan inverse of x/2. So if I take the tangent of both sides, I get the tan inverse. I think that should be a t. We evaluated this at t, so this should be t over 2, not x. We've already evaluated it. Thank you, my mistake. So this should be a t. So now if I take the tangent of both sides, I get the tangent of y2 is equal to t over 2. So now we have a limit in front of this. We have a limit and a 1/2. And then we have the tangent tan inverse of 2 over t. Okay, so what happens to this piece? We're not going to worry about the 1/2 yet. We get the limit as t approaches negative infinity of the tangent of y2 is equal to t over 2. So the right-hand side is going to negative infinity. So this is going to negative infinity. So I need the angle y2 is the angle whose tangent is going to negative infinity. And that is right here. So as you can see, it's going to negative infinity. So the angle I want is negative pi over 2. So y2 is negative pi over 2. So now I have the limit as t approaches infinity of tan in, 2. No, it's a 1/2. I apologize. Is it a 2 or a 1/2? I forget. Let me see. It is a 1/2. Okay, I need a 1/2. A 1/2. Then we had the tan inverse of 0. We said that's 0 minus the tan inverse of t over 2. So that looks like 1/2, 0 minus a negative pi over 2. So I get pi over 4. And as I said, pi over 4 is less than infinity. So this integral converges. Okay, any questions? So that one was a little tough. Okay.
Can you scroll back up?
I certainly can. Where do you want me to go to?
The ending,
Pardon?
the end, like right there.
Okay.
Okay.
All righty. So let's talk about the comparison theorem. Oh, that's not what I want. Let's get rid of that. Let's roll back here. Oh, yes, that is what I want. Go back. We're not doing the comparison theorem yet. I have another problem first. Okay, let's do problem 4. So this one, if you notice, we have the infinity at the top and at the bottom. Okay, so we are going to put t in. So we're going to let this be the limit as t goes to infinity of the integral from negative t to t of x e to the negative x dx. Okay, so now this is doing the same thing as t going to negative infinity, except I am putting in a negative t there for it. All right, what technique from the past that we learned are we going to use to evaluate this integral? x e to the negative x dx. I think I've done this integral 1 or 2 times.
By parts.
Okay, integration by parts. Awesome. Okay, so integration by parts. All righty. And so in order to do integration by parts, I'm going to use my little table only because I like it. I have an x that when I differentiate it goes to 0, so I can do that. I'm going to put derivatives on this side and integrals on that side. So I have x, 1, and 0. Somebody want to tell me what goes on the other side? What goes on the other side of the table? Under the integration side.
E to the negative x.
Okay, e to the negative x. What comes next? I integrate that. So what do I get?
E to the negative x divided by negative x.
Okay, very close. Divided by -1. So it's just negative e to the negative x. Okay, and so then, can you now give me the next one?
E to the negative x.
Good. Okay, perfect. Now we're going to pair these. The first one's going to be positive. The second one's going to be negative. And so now I get the limit as t approaches infinity. And so for this, when I integrate this, I'm going to get negative x e to the negative x, and then I'm going to subtract off the next one, which is going to give me e to the negative x. And that is evaluated between negative t and t. Any questions on the integration by parts? See how we could just throw that in there really nicely? I'm going to factor it. It'll make my life easier. This is the limit as t approaches infinity. I'm going to pull out a negative e to the negative x and multiply it by x plus 1. And then evaluate it between t and negative t. Okay. So I get the limit as t approaches infinity. So for the first piece,
Yeah, hello. I'm sure Prof's network frozen or something. So let's wait for a while. I believe she will join very soon. Okay.
okay. All righty. Things happen. Okay, so this is where we were. So why don't we evaluate them separately? So let's do the first piece. That's going to be the limit as t approaches infinity of, don't have to worry about the negative, but I'll keep it, negative e to the negative t divided by, multiplied by t plus 1. So I'm going to write it as the limit as t approaches infinity. And this is negative t plus 1 divided by e to the t. So I get negative infinity over infinity. And that thing is an indeterminate form. So what rule can I use? If we take the negative out and put the negative in at the end, I don't have to worry about the negative. What rule can I use? Infinity over infinity, 0 over 0. What rule can I use?
L'Hopital's rule?
L'Hopital's rule, okay. So therefore, this is the limit as t approaches infinity. I'm going to get 1 over e to the t. Now, what happens to t? As t goes to infinity, it gets huge, it blows up. Therefore, e to the t gets even bigger and blows up. So what is this integral? In the end, this integral is
Infinity.
okay, who said that?
Analyze.
Okay, so the denominator goes to infinity. So e to the t does indeed go to infinity. So 1 over something that goes to infinity equals what, Annalise?
Isn't
It's
that a
the
rule?
biggest thing ever. You're divided by something so huge. What is the whole thing becoming?
0?
0. Okay, so this limit is 0. Okay, that was very good. So you have to think not just in terms of what the e to the t is doing, but the fact that it's in the denominator. Okay, so now let's do number 2. That's the limit as t approaches infinity of e to the t times negative t plus 1. So we already know e to the t is going to infinity. And then negative t is going to a negative infinity. So this whole thing goes to negative infinity. Okay, negative infinity is not a finite number. All right, it's a less than infinity, but it is not a finite number. Okay, so therefore, when I go back and look at this integral, this piece goes to 0, but this piece goes to negative infinity. So therefore, this integral does not converge. So this diverges. Okay. All righty. All righty. So now let's look at the comparison theorem. And this is actually going to be real important for us as we move forward. The comparison theorem, we're going to use it not only for integrals, but we're going to use it for series as well. Okay, so suppose I have the integral. So suppose I have f of x is less than g of x. So I have one function that's that's basically underneath another function on the interval from a to infinity. So that's from here on. And then I know that the integral from a to infinity of g of x is finite. This integral is finite and it converges. then the integral from a to infinity has to be less than the integral from a to infinity of g of x. And that we know is finite. So when that happens, that says that since this integral converges and this integral is less than the convergent integral, this one converges as well. Okay, so that's the first piece. The second piece is like unto it. So the second piece of the comparison theorem says if f of x is less than g of x, but this time we're on the interval minus infinity up to some b. Okay, same principle. And the integral from minus infinity up to b of g of x is a finite integral, but f of x is less than g of x, so the integral is less, but g converges, so the integral of f of x will converge as well. So this integral converges. So the integral of f of x dx converges as well. Okay, any questions? All righty. Again, I am posting these notes for you. Okay, now this says, suppose you're bigger than something that diverges. Okay, what happens? All right, so now I have the case f of x is still less than g of x, but the integral of f of x goes to infinity. So this diverges. But because g of x is bigger than f of x, this integral dx diverges as well. Okay. And the very last part is on the interval. My goodness gracious, tongue twisters today. Okay, this is on the interval, got that right, minus infinity to b. So again, if f of x diverges and g of x is bigger than it, then this integral of g of x diverges as well. Okay. All righty. So I think we have time for one example for sure. Yeah, we definitely have time for an example. So let's compute this integral. All righty. Now we've already looked at this integral once, and we said that this integral, is this the same exact integral? I think so. That's the same exact one as we did up here. Oh no, that one we went to 1, this 0, this one we're going to 1. Oh yes, it does make a difference that this one goes to 1. Okay. All right, so we want to compute this. So we want to use the fact that f of x, we're going to let f of x be the 1 over x squared plus 4. And we're going to let g of x be 1 over x squared. Now, since f of x has a much larger denominator, their fraction is smaller. Okay, so now I have the condition f of x is less than g of x. And I also did this integral back here where it went to 0. And I saw, wrong integral. I saw this one converged. I don't want to go through all of that computation again. I'm going to try to use the comparison rule. So let's see what we can do. So now what we want to do is we have the integral from minus infinity to 1 of dx over x squared plus 4 is definitely less than the integral from minus infinity to 1 of 1 over x squared. But that is equal to the limit as t approaches negative infinity of the integral of t to 1 of x, and I'm going to make that to the -2 dx. So now I'm actually doing the integral of the bigger function. Okay. So that is the limit as t approaches negative infinity. And now when I integrate this, I'm going to get -x to the -1 evaluated between t and 1. So this is the limit as t approaches negative infinity. So I'm going to get a negative. When I put 1 in here, I'm going to get 1. And then when I put t in here, I get t to the -1, so I get 1 over t. Okay. Now we've already said in this lecture, and we've also know that the limit as t goes to infinity of 1 over t is 0. What about the limit as t goes to negative infinity of 1 over t? What does that go to? Anybody? That term also goes to 0. So this whole thing goes to -1, and it is finite. So the integral converges. So by the comparison theorem, not what I wanted to do. By the comparison theorem, that integral converges as well. Okay, so let me just pull up that just a little bit so y'all have some time to write that down. And